Welcome to homework.
Okay, we are told that a hydrogen-like ion has a nucleus charge of plus Ze. That's great. And that it has a single electron outside the nucleus. So this is a hydrogen-like atom. Oh, but I already said that, hydrogen-like ion. And that the energy levels are going to be negative Z squared RH, which stands for the Rydberg constant, over N squared for energy levels up to N. Now we're told to calculate the wavelength transition from the wavelength of an emitted photon from the transition n equals 3 to n equals 2 for helium to helium plus, a hydrogen-like ion. Right, so that means Z equals 1 because we have helium 1 plus, right? Helium plus is helium 1 plus. That's great. And we're told, yeah, n equals 3 to n equals 2. So the way I like to do that is do final minus initial, right? So if we're going to end up with n equals 2, that's our final n. And if we start with n equals 3, that's our initial n, right? So we do final, which will be negative 1 squared, which I'll write it for now, but it's inconsequential, RH over final, which is n equals 2, 2 squared, minus initial. So this will be minus 1 squared, again, RH, over, and then the initial was 3 squared. Okay. And this is going to give us some value, depending on what kind of RH we use. So we can do RH in joules, which will give us 2.178 times 10 to the negative 18. If they want it in wavelength, then it may be more useful to have the Rydberg constant in terms of wave number, which will give us an inverse units of inverse meters. So in that case, the Rydberg constant is equal to 1.097 times 10 to the 7th meters inverse. Sorry, and the units here are joules. Great. So it'll be more useful for us to use this form of the Rydberg constant. And then we can just calculate what we have here. I see -1 or negative, and then this is, in parentheses. That negative is not going to go away from the squaring. So negative 1 squared, 1 squared is 1, so RH over 2 squared is 4, minus negative, and then 1 squared is 1, so just RH over 3 squared is 9. Okay, so this is looking like negative RH over 4 plus, right, because the negatives will cancel, RH over 9. Great. So 1/4, negative 1/4 plus 1/9. We can put these over a common denominator if we want to do it by hand. So that would be, let's see, common denominator would be 36. So we'll do negative 9 RH over 36 plus, this will be 4 RH over 36. And so we're going to get -5 RH over 36. Okay, so the energy difference between n equals 3 and n equals 2 is 5 RH over 36, or 5/36 times RH. Okay, and then if we sub in what we know to be RH, 1.097 times 10 to the 7th. Inverse meters. we will get the following. 5 divided by 36 times 1.097. That'd be 0.1524. 0.1524 times 10 to the 7th meters inverse, or 1.524 times 10 to the 6th meters inverse. We could also write. Okay, now recall that what we have just calculated is 1 over wavelength, right? We've got inverse meters here. So 1 over wavelength is equal to everything we just calculated, that negative z squared r h over n final minus negative z squared RH over n initial. So we need to invert this, or we need to take 1 over this, or we need to take the reciprocal of this to get wavelength. Raised to the negative 1, raised to the negative 1. So wavelength is going to equal 1 over 1.524 times 10 to the 6th meters inverse. That makes sense because we'll get meters out as our final unit. So what is 1 over this? 1 divided by 1.524 E6. And we get 6.5617 times 10 to the negative 7th meters. Recall that nanometers are 10 to the 9th, so you could think of these as being hundreds of nanometers, or 656 nanometers. Okay, so what range? So that's our final answer. That's the wavelength. But what range of the of the visible or IR spectrum is that? Visible spectrum wavelengths. If we look at a chart, this should be somewhere near red. And yes, 656 is well into the territory of red, which ranges from 740 to 625. So since we're right in there, red is the area of the spectrum.